In this video, we are going to discuss the mechanisms for imine and enamine hydrolysis. So let's imagine you have an imine or you have an enamine. When you react with water and acid, we're going to imagine reforming a carbonyl at the carbon where the nitrogen of your imine is bonded or the nitrogen of your enamine is bonded. So in each of these examples, we're going to form the same carbonyl. We'll imagine essentially severing that nitrogen attachment. That will be kicked out in the mechanism as a nitrogen leaving group. And odds are, that nitrogen component will end up positive in solution and fully protonated. Okay, what this is going to involve is a mechanism where we proceed through tetrahedral intermediates. We're going to need to kick out a nitrogen atom leaving group, and we reform the carbonyl at the carbon where the nitrogen of your imine or your enamine is bonded. We'll first go over imine hydrolysis and then enamine hydrolysis. So here we're starting off with an imine, and we're reacting with water and acid. Mechanistically, the first step is going to be to protonate the imine nitrogen. That forms our iminium-ion intermediate, which is very analogous to a protonated carbonyl. Water is then going to attack the carbon of your iminium-ion, breaking the pi bond. Then we need to deprotonate the oxygen atom to stabilize its linkage in the tetrahedral structure and decrease its leaving group propensity. That brings us to a neutral tetrahedral structure, which we've called the hemi-aminal intermediate. And because we're reacting with water and acid, we're ultimately wanting to kick out the nitrogen component, but before we can kick it out, we need to protonate the nitrogen, charging it positively. We need to protonate it so that we can ultimately kick it out as a neutral amine. And that step there, we're kicking out a neutral amine leaving group by collapsing the lone pair from our OH. That forms a protonated carbonyl. Then water would come in and deprotonate the oxygen atom directly, forming your neutral carbonyl. And then more than likely, your amine that you kicked out, which was kicked out neutrally, that nitrogen is going to grab a proton from hydronium in solution and become a protonated amine. Okay, let's recap that. Very first step is to protonate your nitrogen atom of your imine. That then creates something analogous to a protonated carbonyl. Water will then attack and bond, breaking the carbon-nitrogen pi bond. We then need to deprotonate the oxygen atom, making that neutral. At this point, we have a neutral OH and a neutral nitrogen component. We then need to protonate the nitrogen, charging it positively, so that we can ultimately kick it out in the next step as a neutral amine leaving group. And we kick out the neutral amine leaving group by collapsing an OH lone pair, forming a C double bond O that's protonated. And then finally, we can deprotonate at the carbonyl oxygen atom using water. And then odds is that we had kicked out our neutral amine, but we're ultimately going to probably protonate that, creating a protonated amine and our carbonyl. All right, that is imine hydrolysis. Now, looking at enamine hydrolysis, the mechanism is identical after step one. What we need to do in step one is this. We need to collapse a lone pair from the nitrogen, forming a carbon-nitrogen pi bond, and then we need to break the carbon-carbon pi bond. And in that step, you're essentially bonding the alpha carbon to the hydrogen from hydronium. This hydrogen here is being added to the alpha carbon. Kind of a goofy arrow push. Let's recap that arrow push. We need to collapse a lone pair from the nitrogen, forming the carbon-nitrogen pi bond, and then we're going to break the carbon-carbon pi bond, essentially protonating the alpha carbon in that step. Now that we've protonated the alpha carbon and we have this iminium-ion intermediate, water will attack and break the pi bond. We then need to deprotonate the oxygen atom, making that neutral. We're at the hemi-aminal. And we then need to conceptualize it protonating the nitrogen atom to create a neutral nitrogen leaving group. I will then collapse a lone pair from my OH, kicking out my neutral amine leaving group, which looks like that. And finally, I deprotonate the oxygen atom, and that forms my neutral carbonyl. And odds is that we're going to have that neutral amine leaving group grab a proton from hydronium in solution to create a protonated amine. Okay, going to recap that one more time. Enamine hydrolysis. In the enamine stage, we are going to collapse our lone pair from our nitrogen atom, forming a pi bond. And then we push electrons from the carbon-carbon pi bond to the proton of hydronium, which is forming our carbon-nitrogen pi bond and adding a hydrogen to the alpha carbon. From there, water will attack and bond, breaking the carbon-nitrogen pi bond of your iminium ion. We then need to deprotonate the oxygen atom and stabilize its linkage in the structure and decrease its leaving group propensity. We then need to protonate the nitrogen atom, which increases its leaving group propensity, making it the best leaving group in the tetrahedral structure. And then we'll then kick out the neutral amine leaving group by collapsing a lone pair from our OH component, and finally deprotonate at the oxygen atom to form our carbonyl. Okay. So very similar mechanisms after the first step. And I think the trickiest part with your enamine hydrolysis is just visualizing the air bushing of that first step. For imine hydrolysis, that first step, a little bit more intuitive because that nitrogen has a lone pair that we can protonate directly. All right, but in each case, we could have an imine or an enamine react with water and acid, and we can reform a carbonyl at the carbon where that nitrogen was bonded in your imine and or enamine, and we sever out the nitrogen component, which will ultimately end up protonated in solution.